Thank you. So this is higher Bruhat orders and higher operads. This is joint work with Vadim Schechtman. Conceptually, operad, it's a family of sets of n more equals 0, and On is interpreted as a set of abstract n-ary operations, and together with some structure maps. So maybe I will begin with example. So denote S. This is Cartesian category was object are finite sets identified with just elements n. And then consider permutation groups. For n. And then composition map. Gamma n, m1, mn. So it sends Sn on Sm1, Sm2, Smn to Sm1 plus Mn. And so we have permutation sigma here, sigma 1 here, sigma 2 here, sigma n here. And then we do the following. So we just take a set M1 plus Mn. So we split it in blocks of size M1, M2, Mn. On each block, we act by the permutation sigma 1, sigma 2, sigma n. And then we permute blocks following to the permutation sigma. So just make permutation blocks following sigma. So we can write the same a little bit different. Oops. So namely, we can just make this pictorially. So we choose the set of, so if we want to present element in Sm in the group of permutation of m elements, so just take m vectors, just like C1, Cm. And if we have permutation like 3 to 1, something like this. So we just read this permutation and then just construct a path from 0 to Xc1 plus Xcm. We just read this permutation, so free. So then we just put Xc free, then 2, then Xc2, and so on. And then we just finish this. So we just draw permutation as a path between 0 and each edge of this path parallel to one of these vectors. And then, so what is operad means. So this is operation. So this is operation means.
Consider non-symmetric operators.
Yeah, non-symmetric operators. So we just first we just now do a little bit differently. So we not permute in each block, but then permute the block. So we start from sigma. We just draw the path, and then for each block, so then somewhere this vector x1 parallel to x1 in this path, and then we just replace. We insert in this block the path which correspond to M1. So for M1, there is, and for sigma 1, so there is its own path. But we just squeeze it, and just this path we insert here. And then we do the same for any other M. So therefore, we just, if we have a set of permutations, so we just we draw them as a set of passes, and then we just insert passes following to the orders, and then we just get a longer path from here to here. And for the permutation, for operad, so we need some axioms, and one axiom is associativity. So that means the following. So if we have, so pictorially, so if we have like, okay, so maybe just we can draw it like this. So just we have this is gamma n, m1, mn. So it is gamma n. So this is like n. So it's just one enter, n outputs. Then in each there is m1, mn, and then that's just like n outputs. So this is exactly this. So this is n. It's correspond to this permutation to this path. Then there's the guys. They correspond to this sigma I. So we just insert there, and then we just have such diagram. But now for each node here, we can continue. So that means that we just in each path here, so we can also insert its own groups S, K, I, J, and then we get just a longer path. So just first, so then we can just do the following. So we have just path, this path, then M passes here. So we just insert here, but then in each path we can insert its own group. Then we just insert here, then we get a longer path, but then we can do this into the, one way is I explain, and another way is just to do this other way around. So first insert here, and then longer passes just insert here. So this is associative. So we can just draw this like a picture. So then we can just first do this, or we can do like picking this picture, do this, and this identity. So if if identity is just permutation group in this example would be from one element, so that means just the vector. So if we just insert vector, then nothing happens. Vector remains the same. So it's nothing changes. So generalization of permutations. One can think of generalization of permutations as first example like hyperplane. arrangement in plane, but not central, but hyperplane arrangement in general position.
Affine or projective?
It's what do you mean? So just in plane. Yeah. So plane. Affine plane on atop.
Hyperplane's line arrangement.
Yeah. So it is okay. So it is a line arrangement in atop. Yeah, but at hyperplane, line is hyperplane, so there is no contradiction.
In plane. Hyperplane in plane.
Okay, I agree. Okay, line arrangement in atop.
Hyperplane in line, you know, it's point.
Line in
Hyperplane in line.
yeah point.
Yeah.
So we have hyperplane arrangement, some arrangement. General position means that only two planes can intersect in one point, so not three. All lines, yeah. Lines can intersect in one point, and so if we have n lines, so we just denote it like hn, and now we want to do some kind of insertion. First, we look on the normal vectors to these lines, and then we just put them like in permutation. So we just order normal lines, and then we have 1, 2, n. And then, so hyperplanes lines get number with respect to this number of normal vectors. So then it would be in this.
So coherent and they go in some direction goes in some half plane.
Yeah, in some half plane. Okay. So then you will get something like maybe 1, 2, 3, 4, 5, 6, something like this. 7. And we consider with even
not oriented.
coordinated. So we choose normal vectors.
But why in half plane?
What?
No, direction on this.
So the direction. So you choose direction. Just
All go up.
go up.
You orient in such a way that
Yeah. And then I just put numbers with respect to such orientation, and then I will interest in even number of lines, and then I have so if I have 2n and just first simple operation, and I have another arrangement. Let's say
You have 2n lines, not n here.
2n even. Then
Yeah, I think
it has to be L
drop
even.
each with 7. Yeah.
Okay, so then I will add one more. And then I get another line arrangement with M1. And then I want, so then it would be Mn, so N line arrangement. And now I want insert this line arrangement in this arrangement in some similar manner as I inserted passes in the pass. So how I will do this? So I just take lines 1, 2, just look where they intersect. Just take place 1. So this was like 1, and this was 2. So just look at this point of intersection 1, 2. Just make it small neighbor about this point. Then take this arrangement, and then look on these intersection points. They are finitely many, and they are not too far. Then I just look at the ball, which contains all the intersection points. Then take this ball, they are just insert here.
But here's the 2 directions on the left, and there's no 2 directions on this.
What?
Yeah, it's
just explain so how. So first I just withdraw these two lines,
Yeah, okay.
and then I insert this arrangement in these 2 points, in this intersection.
It's the arrangement is the same plane, so you parallel transport or.
So this is yeah. So how I will insert? So I just look on this line. So there is some last here M1. So M1 will go to
To extreme, yeah.
yeah. I will just put to 2,
Left most.
and then I will look. There is 1, and then I just do the following. So I will take M1 and 1, and I will take all other. So this is vector combination here. So I will just draw them like this one. So this would be like M1, and all other would be very close to this one. So just put it, just draw this arrangement, just that they have vectors very, very close to.
But it's the same thing as you take affine transformation such that.
Yeah. Because it just
Two lines.
Because I can choose as I want. So therefore, just only so how I choose it, I just do this, and then I insert here. Then the next H2 I take 3 and 4. This point, I insert this and this.
Yeah, but then you should extend your things from the neighborhood of the point, which things are very parallel to the second line, yeah?
Yeah, so here it would be, no, second is just this M1.
No, maybe just the first line will have plenty of.
Plenty of, very close.
And when they go outside, it will be still generate position.
Yeah, in general. Yeah, so then I just do this. And then, so how it was in the operads, so I just take map from N, and this is M1, Mn, from object, so I just take On on M1, Mn, and this is what goes to M1 plus Mn. But in this example, what happens, so we have a map from 2n, and then we have M1, Mn, and it is from O to N on O M1, O Mn, and this goes to O M1 plus Mn. So in some sense, so we just replace so here for each element we just put instead of this element we just put this one.
You here implicitly assume that Mi is at least 2.
Yeah. So this is So this in this case, so we will consider category with n more or equal to.
I thought it was greater equal to 0 even, yeah.
It may, it was even more than 0, But here we have a restriction.
So it started from 2,
Yeah.
Sorry, where you have 2m and
2n. And in each plane, you need to replace pair. And you have to replace pair by something which pair plus something, or at least pair. So just take intersection 2. And so therefore in this, so plane arrangement of lines has to have at least 2. So 1 is not.
But why you have 2n and not just n?
Because you have to in order to replace, you have to take two lines. You have to withdraw 2 lines and insert something instead of 2. And then
you just split all your lines in pairs and you replace
I have n pairs, for each pair.
So you
but now we need
inserts from lines 1, 2 and 1, 3. You never just like that.
For operation, no. So generally, you can insert. So you can choose some other way to splitting them. But in sense, in any case, you will just choose. But just to define operation, then you will define another operation.
Okay.
But just to understand the operation, in any case, you need 2n instead of n. And associativity will now also a little bit tricky in this case. So because what means associativity? That we have possibility to insert in M1. But then M1 has to be even. Yeah. So therefore, associativity is a requirement for the map from 2n to M1 to Mn. So therefore, if you have such a map, and then you have this, then associativity have to hold with such replacements. And so therefore, this is example, and then sorry. And then it's clear how it's defined for any d. So we define definition. So we have some monoidal category with n or equal d. And we call operation, so we have operation dn, m1, dm1, no, okay, so m1, mn, which send o dn, and o m1, o mn, to o m1 plus mn. A d-operad if it is associative, it is d-associative. That means that we can compose dn, dm1, dmn with gamma dm1 dk11 tratata dk1m dmn dk1n tratata dk n1 n mn. And so we can just make correct such a composition, and this unit element in O of D. So unit element, so if it just means that if we take, so unit element I, so it means that if we just take O dn, and here we have O of D, O of D, and here just so it goes to O of dn, and this is identity map. So if we just put here, so in O of D it could be more than one element. But there is some element here, so if we just put here I, then this would be identity map. Yeah. Okay.
Yeah, but it looks at an axiom use only indices divisible by D.
Yeah.
And if you consider redefine U, you get this usual definition of operad here.
Yeah. So so if D is equal 1,
No.
What is it?
Because if you keep only O within this, depending on number divisible by D.
Yeah. No, it would be not operad.
No, I see this. All your things it's written like it's you get an operad.
No, because it's here it's dn,
Yeah.
and here it's would be also dn. So we just put d. M1 dmn, and here it would be d.
Yeah, and
But
Well, letter D, it looks like an operad. Yeah.
no, in operad you have to you get here d squared something.
No. You define new operad
Yeah.
whose n space will be ODN for your d-operad. You denote like O tilde n. Yeah, this denotes things. Then it looks at your map and axioms will be exactly associativity. Because in axioms you don't really use O. This index is not divisible by D. It will be some.
No, something. Okay.
yeah, maybe.
Yeah. So yeah. So this I will just maybe there is some difference. I cannot immediately answer to your question, but just maybe later. Yeah. So now, so what we want, kind of generalization of this. So from line we can go to hyperplane arrangement, but also to pseudo-hyperplane arrangement. And pseudo-hyperplane arrangement, so they related to the higher Bruhat orders. And what we want, also just a small remark that if we have this operator with symmetry group, then on the permutation there is Bruhat order. So then we have this map gamma n, m1, mn on symmetry group. Then we just map Sn, Sm1 on Smn to S of m1 plus mn. Then on each on Smi there is Bruhat order on permutation. So if we look on the passes, then so if we have just imagine that we have a pass like this one, so if we have like a corner like this one, so we have just two consecutive edges which looks like this one, then it means that what is that this vector is bigger than this. So this number for this vector is bigger than this number. So therefore, such a corner correspond to inversion in the permutation. And so then we can just make a flip. So we just replace such inversion by no inversion. And then we say that two permutation sigma and tau, sigma is less than tau if sigma can be obtained from tau by some sequence of such flips. So this would be Bruhat order on permutation. And then, so observation is that, so if we have sigma on sigma 1, sigma n, and if we have sigma, this map, so this just go here on tau 1, tau n, and if we have this in Bruhat order, in these elements, then the result will be also ordered with respect to Bruhat order in this group. Okay, so now higher Bruhat orders.
Sorry, and for, sigma is the same.
Yeah, for sigma, yeah, sigma is the same. So on sigma, it doesn't. Unfortunately, so we cannot do this universally. So sigma is, in some sense, it's in these pictures, it's just permutes blocks. So in each block, it follows. But if you just between blocks, so there is no any control. So high Bruhat orders. So they define it on the so D order is defined on discrete Grassmannian. So Grassmannian D of n. So we just take set of n elements, and so this is a set of all D element subsets of n.
People denote it also by binomial.
Yeah. So it's this binomial notation. So in this, so maybe some quantum sometimes, but I will not use quantum. And so and then we denote by a dn a set of linear orders on this set, which satisfy such condition. So we take any d+1 element subset E1 ed+1. So Vadim Schechtman call such subsets pocket. So this is pocket, and then we consider all d element subsets which obtain it, but we just put them in the following. So we just kill E1, so then it would be E2 ed+1, then it would be E1 E3 ed+1, and so on. And at the end we just kill the last element ed. So we have such d +1 element subsets, and then so this linear order has to order them either in this manner or in this manner. So if we have d+1 element subsets, then it has to be either this or this order. And then B of nd is just it is the set of refinement of this. So we consider just partial orders. Such which obtained from such linear order by modular equivalence by quotient by equivalence relation. So two linear orders are equivalent. So if we make so we have sigma 1 is equivalent to sigma 2 if on any packet, so they have the same ordering of elements in packet. So either lexicographically or anti-lexicographically. And then this set calls B and D. And then there is analog of this flip. So there is a notion of dense packet. And in dense packet, we can make a flip. So if it was lexicographically ordered, then we can make it opposite anti-lexicographically or vice versa. So one flip called, so if we just go from this to this calls rising flip. And this, if we go vice versa, then it's lowering. And the D order on such set B and D is again like with permutation. So you have two equivalent classes, and then if one class is obtained by a sequence of the lowering flips, then it's smaller than another element. And what was nice theorem by Grassmannians and Schechtman. So this passet has maximal and minimal element, and any element can be joined with maximal or minimal element by flips.
Can be sort of some kind of like a range of matroids, because it looks like you.
Yeah, just 1 second. Yeah. So how it's related with hyperplane arrangement? So Kapranov and Voevodsky they made. So they made a nice geometrical interpretation of the order. So you have to consider zone atop. This is sum of line segments. So you have just these segments, but you have just to put them in d-dimensional space, and then consider sum of these segments, and then make cubical complex inside it from cubes, or vice versa. So for each cube can be understood. So each such direction. In my case, I just consider that it is line, but to each direction you can correspond to pseudo hyperplane, and then you have pseudo hyperplane arrangement, and then the intersection point of this hyperplane will be, so you consider pseudo hyperplane arrangement in general position, and that means that only d of them intersect in one point, and this is exactly would be this element, and then it's just then this packet, that means that you have just this simplex, and then it just the requirement, so you just put this, that means that this point has to be ordered like in this order, so it like 1, 2, 3, and then it means that this point has be either less than this middle point and then the end, or vice versa. So this in this case. Yeah, and now so this is now theorem. So so the set of so the set of B and D can be endowed with a structure, with this structure of a d-operad, and yeah, so it's some more tricky, have to be more tricky arguments than just in with hyperplanes. But what is just I want to say, what is difference between in this example, difference between d-operad and usual operads. So so if you have set n, choose d1 on n, choose d2, so you have dn to d, and now you have dn1 to d. So if you just and all other just identical, so just consider composition of you just want to just in this case, so you have in this product you have O of dm1 and all other OD, 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 so just identical. But if you just look on the number of elements, then the number of elements in dn1, so then we just insert, then it would be dn1 just plus minus d. Just 1 second, so it would be d n1 plus n minus 1. Yeah. And so here we have much more elements than here, and that means that in order to define, so we not only just insert like it was with hyperplanes, with planes, with lines in the plane. So then we insert, then it appears some intersection points, new intersection point. But due to construction, in some sense, they automatically was ordered. So we just get this just by free. And so in general, in the d-operad, so it might appear more elements on which we have to define something like this Bruhat order. So we not only insert one set, one Grassmannian instead of another Grassmannian, but there's some extra points, and then we have also this order have to be defined on some extra points. So therefore, there's some feeling that maybe the argument is not exactly works, but just I have to think probably it was not so simple. Okay, so maybe I have to stop here.
Oh, great. It's a time for questions.
To be correct, is this B and D something larger than certain cells in Grassmann? It seems relative to actual configuration of hyperplanes here.
Yes, it's in general conditions.
Yeah, in general.
It's some special cell, like big cell.
Big, yeah.
Yeah.
Another question or comment?
Do you know some properties of this operator?
No, only we have some examples. So it's just beginning.
Causality or something?
Yeah, this we just plan to look on this. Just what would be from usual operad goes in more general this step. Just only it was because we just first want to generalize it. Yes, because there is some order on the permutation, then it seems that we can just operad obtain like higher Bruhat order. But then it occurs that it does not work because we have increased this number, so it just always there's a straight between n and dn. So then we start from n, then it's just only from this order n and preserves. So it's just you have, and so therefore we just find another way. But it was idea that maybe just higher Bruhat order, just idea how they define it. Just we consider this and then consider order some. Maximal chains, but unfortunately it doesn't work.
Okay, if there are no other questions or comments, we thank the speaker and the participants.